Bismillahirrahmanirrahim. Assalamu alaikum students. I hope you are fine and must be busy with all of your life activities. Now class, our today's topic, we will discuss that what is a transportation model and what is the purpose of transportation model. As its name refers that this method is used for a sort of transportation plan to be made by the operations manager in order to minimize the cost. Every organization is having the different sort of factories and they want to supply their products to the different destinations. So they are always interested to find a sort of transportation plan so that they can achieve their objectives within the minimum possible time and especially within the minimum possible cost. So we will discuss this important topic in detail, that how this linear programming method will also guide us that how we can achieve this sort of objectives in the operations settings. Then we will discuss some real life applications, that what is actually the objective of these transportation models and how the operations manager can achieve their objectives, that is the minimization of cost by using these very important techniques. So again class, the mathematical techniques or the statistical techniques which we usually use in operations management, their practical implication is so important, that how we will apply those techniques in the real life in order to take the better decisions. So that is actually the objective of this subject also, that we'll have to discuss that how we can apply the different situations into the real life in order to achieve the particular objective. So we will discuss this transportation model in detail, that how we can have the different alternative plans for transporting the goods to the different locations, and how we will be able to minimize this cost. So after discussing these sort of techniques, of course will be so after discussing this technique, we will be able to formulate an optimal transportation plan. And in this particular method we will also discuss that how we can achieve some initial solution. You must remember that in the simplex methods and in the graphical methods we try to achieve some initial tableau or initial graph. In this method also we will try to achieve some initial solution, and then we will use the step-by-step approach or the algorithm in order to improve that initial solution. So we will discuss the different concepts and the different techniques which are used in that transportation model in detail. The transportation model is also one of the technique of linear programming method. It is a subclass of linear programming method, and again in every organization there are some origins or the factories or the locations from where the goods are to be transported to the different destinations or different target points. And again the transportation manager or the operation manager is always interested to minimize the cost of transportation from the different sources to the different locations. So that is what about the transportation problems and the transportation method we will discuss in this particular topic. So transportation problem is one of the subclass of linear programming problem. So students, it is also a type of linear programming technique where the objective is to transport the various quantities of a single homogeneous product that are initially stored at various origins to different destinations in such a way that the total transportation is minimum. So that is the main definition of a particular transportation model, that we are actually interested to transport our goods from the different sources or from the different origins to the different final destinations at the different locations. And we want to have a sort of plan so that we can transport all of these goods to the different destinations with the minimum possible cost. So that is all about the transportation model. Okay students, the purpose of transportation model is again the minimization of cost Mostly we are interested in the minimization of cost in these sort of models and the problems, but may also be interested to minimize the time of transportation. So these are some of the objectives we would be able to achieve after learning these transportation models. So transportation models or problems are primarily concerned with the optimal or the best possible way in which a product produced at different factories or plants called supply origins can be transported to a number of warehouses called demand destinations. So in which particular situation we are interested, that we want to transport our goods from the different sources to the different destinations. The objective in a transportation model is to fully satisfy the destination requirements within the operating production capacity constraints at the minimum possible cost. Okay class, you must remember that when we were discussing the linear programming problems and when we were solving the related problems, first of all we make some objective function, and then we formulate some inequalities or the equations in order to represent our constraints. So the similar constraints may prevail in this sort of transportation model, and these constraints are related to the supply as well as the demand. There's some supply capacity of every factory in the different organizations. So of course we cannot work above that particular capacity. So that's why these are sort of supply constraint we'll have to deal while we are making any transportation plan. Another constraint which will be discussed in this particular transportation model is the demand constraint. That is the demand of the different destinations, and of course we want to fulfill the demand of the different destinations through the transportation of our products. So we want to fulfill both of these constraints, that is the supply constraints as well as the destination constraints, in order to achieve our objective, that is the minimization of cost. So again, like the linear programming problems we have just discussed in the previous lectures, in this transportation model there will also be an objective function. There may be the different cost rates, but the method of solving this transportation problem may be different from that of the linear programming problems. But this is a type of linear programming technique. The objective in a transportation problem is to satisfy the destination requirements within the operating production capacity constraints at the minimum possible cost. So students, let's suppose there are the different sources or the origins, or we can say the units of supply through which we will have to supply the different goods to the different destinations. Suppose there is an A1 source, or there is an A2 source, or the A3 source up to AM source, which are being prevailed in the organization. So these are actually the different supply points or the origins or the factories from where the goods are to be transported. So these are the different sources of supply. Then again, there are the different destinations. Suppose there is some B1 destination in some location, there is another B2 destination at some other location, similarly B3 destination at some other location, up to Bn destination at the different locations. So these are the different demand destinations whose demand is to be fulfilled by the organization. So these are the different sources, and these are the different destinations. Now we can have the different plans of transportation. If we want to fulfill the demands of the different destinations, what we can do, we can supply the goods from source 1, that is A1, to the destination 1, that is B1. We can also supply our goods from the source 1 to the destination 2, or the B2. We can also supply from the source A1 to the destination 3, that is B3, and we can also supply this product or the service from the source A1 to the destination Bn. So these are the different alternatives. Similarly, we can also supply from the source A2 to the source 1, that is B1, then again from the source A2 to the final destination B2, from the source A2 to the final destination Bn. The same is true for this source of supply, that is AM. We can supply the goods from this source AM to the destination B1, from this source AM to the destination B2, or from this source AM to the destination Bn. So these are actually the different alternatives which the operation managers can use in order to transport their goods and services from the different sources of supply to the different destinations of their requirements. Then again, class, we cannot supply all the quantity of the goods from a particular source to the particular destination because of the different supply constraints as well as due to the different demand constraints. So what we do, or what the operations manager will do, he will supply a particular quantity from the one of the source to one of the destination. Now suppose that X11 again is the quantity from that is being transported from source A1 to the destination B1. Similarly, let X12 be the quantity that is being transported from the source A1 to the final destination B2. So this X actually shows the amount or the number of product that are being transported from a particular source of supply or factories or origins to the final destinations. Similarly, when we will transport the goods from a particular source to the special destination, it will bear some cost. So this cost is being represented by that C11. Again, C11 indicates that this is the per unit cost for transportation of the goods from source A1 to the final destination B1. So that is the subscript 11 indicates the source 1 to the final destination 1. Similarly, C12 will indicate the source 1 to the final destination 2, and in the same fashion the CMN will indicate the cost of transportation of goods from the source M to the final destination N. So this is all about this transportation scenario, that we will have some origins or the factories or the sources of supply for the organizations, from where we will have to transport our goods to the final destinations. Then again, we will have to identify the different costs of transportation from a particular source to a particular destination, and again we will also have to identify the number of products which are to be transported from a particular source to the particular destination. So we can have the different alternatives. But again, class, in this practical scenario, actually we are interested to find out a sort of transportation plan so that we can minimize our cost. So this is our main objective in this sort of problems. So students, in the next step, what we will do, we will convert that real world situation or the information in the form of a table. So this is the table which is actually representing the transportation model information. You can see on your left hand side there is a column about the sources. In this particular case there are three sources, that is S1, S2, S3. Again, these are the sources of supply, or these are the origins from where the goods are to be transported. In the uppermost row you can see the different destinations, that is destination 1, destination 2 and destination 3. So these are the final destinations to which we are interested to supply our products and services. And again, class, the capacity of factories or the sources of supply should also have been mentioned in this particular graph. You can see that the capacity of this source or factory S1 is represented here as C1. So we cannot produce above that particular quantity of C1. Similarly, the capacity, the full capacity of the source S2 is represented here by C2. Similarly, the capacity of source or factory S3 is represented by C3 here. Again, there are some requirements on the part of the different destinations. So these requirements again should be shown in this table. The requirement of the destination D1 is represented here by small d1. The requirement of destination capital D2 is represented here as small d2, and the requirement of destination capital D3 is represented here small d3. So in this particular cell, what we will do, we will add all the capacity of the different sources, as well as we'll also add the demands of the different destinations, so that we can have a total amount in this particular cell. And so this particular cell will show us the total capacity of the organization, as well as the total demand on the part of the different destinations. Next class, here you can see Xij is the quantity of a particular product to be transported from the source S1 to the destination D1, and Cij is the unit cost from supplying a particular product from source S1 to the final destination D1. Similarly, Xij shows the amount to be transported from source S1 to the final destination D2, and in the upper right corner you can see Cij, that is the unit cost which the organization will have to bear for transporting a particular product from the source S1 to the final destination D2. Similarly, this Xij is the amount to be transported from source S3 to the final destination D3, and Cij may be the cost for transporting the good from the source S3 to D3. So in this particular way, we'll have to interpret and we'll have to understand this particular table, that what are the different sources, what are the different destinations, what is the capacity of a particular source, and what is the demand for a particular destination. Then again, what is the unit cost from any of the source to any of the final destination, as well as we'll also take into account the quantity of the product which is to be transported from a particular source to a particular destination. So this sort of information we will discuss in the transportation models, and again we will try to have some initial solution, and again after that initial solution we will try to have some optimal solution, that how we can have a transportation plan so that our total cost may be minimized. Let Xij are the units to be transported from source I, where I is equal to 1, 2, 3 up to m, or up to any other number. So these are the different sources of supply to the final destination j, where j is equal to 1, 2, 3 up to any particular number. So these are the different destinations. Cij is the cost to transport the goods from source I to the destination j. So as we just discussed, that this C represents the unit cost in transporting a good from a particular source to a particular destination. After substituting Ij with respective numbers, the previous table will become like this. So if we substitute these subscripts, that is 1, 2, 3 in our previous table, we can have this sort of table. That is, again, there are the three sources S1, S2, S3. There are three destinations D1, D2, D3. Now we have substitute those subscripts in place of I and J. So X11 is the quantity to be supplied from source S1 to the destination D1, and C11 is the cost of the transportation from the source S1 to the final destination D1. So it is very important to understand these subscripts, that from which source to what destination we are referring when we will target a particular cell in this particular sort of table. So class, C11 is actually the cost for the transportation of goods from the source S1 to the destination D1. So this first one is showing the source and the second one is showing the destination. In the same way, this capital X32 indicates the quantity of the product to be transported from the source S3 to the final destination 2. So this 3 is actually representing the source, and this 2 is actually representing the final destination. So in this way we'll have to interpret this particular table. And again, C1 is the total capacity of source S1, C2 is the total capacity of source S2, C3 is the total capacity of source S3. Similarly, the total demand for the destination D1 is small d1, for the second destination is small d2, and for the third destination is small d3. And again, we can have the totals for this particular row and the column, and we can have the total capacity and total demand. Class, let's consider an example in order to understand that particular transportation problem. Suppose PowerCo has 3 electric power plants that supply the electric needs of 4 cities. The associated supply of each plant and demand of each city is given in the table. So in this particular example, we have 3 sources, that is the sources of electric power supply plants, and there are 4 destinations to which we'll have to supply the electricity. That is and these are the 4 different cities. So these are the 4 destinations actually. So class, let's interpret this sort of table. Now this is the sort of situation which you already have in order to solve the particular transportation problem. Now, as we discussed, there are 3 sources of supply in this particular case, that is plant 1, plant 2 and plant 3. So these are the different sources of supply through which or from which we'll have to supply the electricity to the 4 of the cities which are actually the 4 destinations, that is city 1, city 2, city 3 and city 4. Now again class, you can see the different figures in these particular cells. What are these figures about? The $8 means that the unit transportation cost for supplying that electricity from plant 1 to the city 1 is $8. Similarly, $6 is the cost of transportation for supplying the electricity from plant 1 to city 2. Similarly, $5 here is the unit cost of transportation from plant 3 to the final destination city 4. So these are actually the unit costs which are being given here in order to supply the electricity from the different sources to the different destinations. Now let's see about the total capacity of the different plants. Plant 1 has the total capacity of 35 million kilowatt hour. Similarly, plant 2 has the capacity of 50 million kilowatt hour, and again plant 3 has the total capacity of 40 million kilowatt hour. So these are actually the 3 constraints that we cannot supply more than this particular capacity from our plants. So that is the limitation on the part of that electricity plants. Similarly, city 1 has the total demand of that 45 million kilowatt hour. So this is the total demand of the particular city 1. Similarly, city 2 has the total demand of 20 million kilowatt hour. City 3 has the demand of 30 million kilowatt hour. City 4 has the demand of 30 million kilowatt hour. And if we go to add these particular values for this particular column and this particular row, we will get the total amount as 125. And in this particular situation, the total demand is equal to the total supply. So that is one of the situation which we are discussing in this particular problem. So students, now you are well aware of that what is this table about, and what the different values in this table shows. A transportation problem is specified by the supply, the demand, and the shipping cost. So again, as we just have discussed, that we should formulate a sort of table in which we'll have to identify the supply, we'll have to identify the demand, as well as we'll have to identify the cost of the transportation of the goods from the particular supply to the particular destination. The relevant data can be summarized in a transportation tableau. So this sort of tableau we have just discussed. The transportation tableau implicitly expresses the supply and demand constraints and the shipping cost between each demand and supply point. So class, it is very important to formulate this initial transportation tableau, and we'll have to identify that what are the different demands of the different destinations, as well as what is the different capacity of the different sources of supply, and also we'll have to identify that what is the per unit cost of transportation of the particular product from one of the source to any of the destination. So let's discuss the solution of this sort of transportation problem. Since we have to determine how much electricity is sent from each plant to each city, let Xij is the amount of electricity produced at the plant I and sent to the city J. Class, we generally use these subscripts I and J in order to represent the multiple supplies and multiple destinations. In this particular case, there are three sources which may be represented by 1, 2, 3, and there are the 4 destinations, and we can represent that J subscript by 1, 2, 3, and 4. So this is a general way to write the particular value by using that subscripts. So Xij is the amount of electricity produced at the plant I and sent to city J, and X14 is the amount of electricity produced at plant 1 and sent to city 4. Since we want to minimize the total cost of shipping from plants to cities, so class, actually we try to formulate our objective function, and in this particular case we want to formulate our cost objective function, and if we represent that cost objective function here by Z, then it will be equal to summation Cij multiplied by Xij. That is, if we multiply all the relevant costs, unit costs, by the total amount supplied from the different sources to the different destinations, we will have the total cost function. And if we refer to this particular table, then the total cost of function will be like this. That is, Z is equal to 8x11. Now what is meant by 8x11? You can see in this table, if we consider the quantity of electricity or the amount of electricity supplied from the plant 1 to city 1 as X11, then the total cost of supplying that electricity from plant 1 to city 1 will be 8 multiplied by that quantity X11. So that is actually being represented here, that is 8x11. Similarly, for the second cell, $6 is the unit cost for the transportation of good or the electricity from plant 1 to city 2. So if we represent the particular quantity of electricity to be transported or supplied from plant 1 to city 2, as x12, then the total cost of transportation from plant 1 to city 2 will be equal to 6 multiplied by that quantity x12. So again, these subscripts 1, 2, 1, 3, 1, 4 are so important, because this will indicate you that what is your source and what is your final destination. So if we sum up all of these costs from the different sources to the different locations, we will have the transportation cost function like this, that is z is equal to 8x11 plus 6x12 plus 10x13 plus 9x14 plus 9x21 plus 12x22 plus 13x23 plus 7x24 plus 14x31 plus 9x32 plus 16x33 plus 5x34. Again, what is this 5 about? 5 is the unit cost of transportation from the source 3 to the city 4. And what is x34 here? x34 is the total quantity of electricity supplied from source 3 to the final destination 4. So what we did, we add up the total transportation cost from the different sources to the destination, so that we can have a total transportation cost function. As we discussed that there are supply and demand constraints when we are going to transport the different goods from the different sources to destinations. So in this particular case, what is our supply constraint? We have 3 supply constraints because we have 3 supply points, that is plant 1, plant 2 and plant 3. And what is the constraint here? The constraint or the limitation of the plant 1 is the production of 35 million kilowatt hour of electricity. So the plant 1 cannot produce more than this amount of electricity. So x11 plus x12 plus x13 plus x14 should be less than or equal to 35. That is, x11 is the total amount of electricity to be supplied from plant 1 to the city 1. x12 is the total electricity supplied from plant 1 to city 2. Similarly, x13 amount supplied from plant 1 to city 3. x14 is the amount of electricity supplied from plant 1 to city 4. So if we add up all of these quantities, then this sum should not be greater than or equal to 35. It should be less than equal to 35 actually. So that's why we represent this constraint of supply for the first source here. Similarly, there is the constraint for the second source of supply. There is the third constraint, which represents the constraint for our third plant here. And again, we cannot produce more than 40 million kilowatt hour of electricity from the plant 3. So that's why all of the quantities to be supplied from this plant 3 to the city 1, 2, 3 and 4 should be less than and equal to 40. So class, this is our supply constraints. We have represented those constraints again in the form of inequalities. Next is the demand constraint. The company is required to meet the demand of the different destinations, represented in the form of inequalities. Now first constraint in this particular case is for the destination city 1. The demand of city 1 is 45. So the total amount of electricity supplied from the different sources to this destination should be greater than or equal to 45 in order to meet the full demand of city 1. So that's why again, if x11 is the amount of electricity supplied from source 1 to destination 1, x21 from the source 2 to the destination 1, x31 from the source 3 to the destination 1. So all of these three sources are supplying to the single destination, because we are talking about the demand of the destination city 1, and that whole sum should be greater than or equal to 45. That is, we should meet the minimum possible demand of city 1. So this is the particular constraint on our first destination. Similarly, the constraint for the second city can be represented in the form of this inequality. Again, the third and fourth city constraints may be represented in the form of this inequality. So these are the four demand constraints actually, which are represented in the form of inequalities. Again, class, you must remember about the non-negativity constraints, that xij, where I is equal to 1, 2, 3, that is x11, x12 or x13 should be greater than or equal to 0. Similarly, x31, 32, 33, 34 should be greater than or equal to 0. So these are non-negativity constraints, because we are talking about the quantity of product supplied, and of course the quantity cannot be taken as negative. So these are non-negative constraints. So class, we have discussed about that total cost function, and after that formulation of the transportation table, we are able to find out the cost function. Then we are able to represent our demand constraints as well as our supply constraints in the form of inequalities, and we also identify the different non-negativity constraints. Now we can have this sort of problem representation like this. Now you must remember that this is the sort of representation of the problems which we also used in linear programming methods. Here is the cost function which we have just computed, and again we are interested to minimize this particular cost function. And as I already discussed, that this is actually the sum of the different costs from the different sources of supply to the different destinations. And again, we should take into account every possible alternative, that is from every source to the every of the so we should take into account all the costs which will have to be bared for the transportation of the goods from the three different sources to the four of the different destinations. So by summing all of that cost, we will be able to formulate this cost function. And again, there are three supply constraints, and of course our cost function is subject to these three supply constraints. That is actually the constraint of capacity, that our different plants cannot produce beyond this particular capacity. And again, there are some demand constraints which have now been represented in the form of different inequalities. Demand constraints again represents the particular requirements of the customers or the destinations, that at least we will have to supply this amount of or this quantity of product to a particular destination in order to fulfill the demand of the destination. Again, xij is greater than or equal to 0 here, where I is equal to 1, 2, 3 and j is equal to 1, 2, 3, 4, and this represents the sign constraints or the non-negativity constraints. Let's discuss the general description of the transportation problem. A set of m supply points from which a good is shipped. Supply point I can supply at most SI units. So class, if there is a set of m supply points from which a good is shipped, supply point I can supply at most SI units. That is about the destination constraint, that we cannot supply the goods from a particular source to the destination more than the requirement of the particular destination. That is meant by this particular statement. Similarly, a set of n demand points to which the good is shipped, demand point j must receive at least dj units of the shipped goods. So what is meant by that? That we will have to supply at least the amount required by the particular destination, no matter from which source we will supply this particular product to a particular destination, but the total demand should not should meet at least a particular demand requirement. Each unit produced at supply point I and shipped to demand point j incurs a variable cost of Cij. So it means that Cij is the cost incurred for the transportation of goods from supply I to the final destination j. Class, we can have three sort of situations in this transportation problem. First is the balanced transportation problem. That is the situation when we will have the demand equal to the supply, and there is an unbalanced transportation problem situation in which either the supply is less than the demand or the demand is less than the supply. So in our lectures for transportation problems, we will discuss each of these situations. So this is the balanced transportation problem example. If the total supply equals to the total demand, the problem is said to be a balanced transportation problem, as I just discussed, that the sum of the different supplies must be equal to the total demand of the different destinations. So this is the balanced transportation problem. This is the particular example of balanced transportation problem. You can see there are the different three sources, S1, S2 and S3. And S1 has the total capacity of 15, S2 has the total capacity of 25, S3 has the total capacity of 30. Similarly, the destination D1 has the total demand of 10, D2 has the total demand of 20, D3 has the total demand of 40. The total capacity of all of these three sources is 70 units, and the total demand of the different three destinations is 70. So in this particular case, demand and supply are equal. So the next situation is when the supply is less than the total demand. If a transportation problem has a total supply that is strictly less than the total demand, the problem has no feasible solution. There is no doubt that this is the case. One or more of the demand will be left unmet. Generally, in such situations, a penalty cost is often associated with unmet demand, and as one can guess this time, the total penalty cost is desired to be minimum. To solve such problem, we need to introduce a fictitious source to provide the required supply at zero cost or cost provided in the problem. So let's discuss this particular situation with the help of this particular table. Again, students, there are three sources, S1, S2, S3, which have the relevant capacity in this particular column, and there are three destinations which have the relevant demand in this particular row. Now if we sum up the different supply and demand, we can see that the total supply capacity is 70 units here, and the total demand is 80 units. So that is the case when supply is less than the total demand. So what happened in this particular case, if we try to solve this particular problem directly, then it will be not be possible to have a sort of feasible solution. So what we will do in this particular case, we will add a fictitious or dummy source at this particular place, so that we can have a sort of dummy supply from this particular fictitious source as 10. That is the difference between the total supply and the total demand. So in this particular situation, when supply is less than the total demand, what we will do, we will add a dummy supply source here in order to fulfill the demand and supply equality. So we will write the difference of the total demand and total supply in this particular cell in order to have the equality for the demand and the supply. From this situation onward, we will learn that how we can find out the initial solution and then the optimal solution. But at this point, what you should remember, that whenever the supply is less than the total demand, we may have to add a dummy or the fictitious supply here in order to equate the total demand and total supply. So what happens if the supply exceeds the total demand? If the total supply exceeds the total demand, we can balance the problem by adding dummy demand point. So as in the supply case, when supply was less than the demand, we add a supply source. But if demand is less than the supply, then we will of course add a source of demand point, which is actually the dummy demand point. So these are the three sources. These are the relevant capacity of these sources. There are three destinations which have the relevant demands, and again now the demand is less than the supply. So in this particular situation, what we will do, we will add a fictitious demand point here in order to write that particular difference of demand and supply here, so that this total supply and total demand can be equated. So class, this is the particular situations. You must remember that what happens if the demand is less than supply, and what happens if the demand is greater than supply. So how we can find the initial possible solution in this transportation problem? Unlike other linear programming problems, a balanced transportation problem with m supply points and n demand points is easier to solve, although it has m plus n equality constraints. The reason for that is, if a set of decision variables satisfy all but one constraint, the values of this xij's will satisfy the remaining constraint automatically. So class, whenever we have the demand and supply equal, it will always be easy to find out the initial possible solution, and the reason for that particular scenario is that if we have a set of decision variables which satisfy all but any one constraint, then the values of that xij will also satisfy the remaining constraints automatically. So what is meant by this particular statement here, that whenever the demand is less than the supply or greater than the supply, and if you are able to add that dummy supply point or dummy demand point, then again we can have the equality of that demand and supply, and it will then be easy to find out the solution, and that dummy variable will not actually have any effect on our optimal solution. And of course we will discuss this particular case when we will solve the different related problems. So class, there are two methods which are available for finding out the initial feasible solution, and these methods are known as northwest corner method, and the second method is least cost method. So let's have a practice of both of these methods. Now what we do in northwest corner method, we try to begin in the upper left northwest corner for the transportation tableau and set x11 as large as possible. Here the limitations for setting x11 to a large number will be the demand of the demand point A and the supply of the supply point 1. Your x11 value cannot be greater than minimum of these two values. Now what is meant by this statement, class? You know, this is north and this is west. So what we will do, we will start from the very first cell in order to fill a particular quantity there, and we will compare the relevant supply and the relevant demand. Whichever quantity is less, we will put that particular quantity in this first cell. So this is how we will start filling the table by using that northwest corner method. Now class, let's discuss this particular example. Suppose these are the different sources. Now suppose class, there are three supply points here, that is S1, S2, S3. These are the supply points, and suppose there are three destination points, that is D1, D2, D3. Now the supply S1 has the total capacity of 5, that is represented by this particular figure. The supply S2 has the total capacity of 6 units, and the supply S3 has the total capacity of 2 units. So these 5, 6, 2 actually represents the total capacity of the different supply points. Similarly, The total demand of the destination D1 is represented by 3 here. The destination D2 has the total demand of 5. The destination D3 has the total demand of 2, and the destination 4 has the total demand of 3. So when we will try to fill this particular table by using the northwest corner method, we'll have to start from this particular cell. We'll have to start from this particular cell class, and what we will do, we will compare the total supply here and the total demand here, and whichever is in less quantity, we will put that particular quantity here. So what we will put here, that is 3, because 3 is less than that 5. That's why we put 3 here. And again class, as we have fulfilled all of this demand, so we have crossed at this particular point. Now it means that we cannot add any other number in this column, because that will deviate the total destination demand for D1. So this is the north column which we just have filled. Then now we will try to fill this particular row. Initially you can see that the total supply was 5 here, but as we have written 3 here, we will subtract 5. We will subtract this 0.3 from 5. It means we have now the supply available here is 2. That is the 2. So we will just go to the west of this particular cell, and we will write 2 here. So that is the 2. And again, when its supply is exhausted, we will cross this particular supply. Now in the next step, we will put 3 here, because we want to fill this particular cell, and if we compare the particular column and the particular row, you can see that 3 is in the less quantity than 6. So we will just put 3 in this particular cell, that is the 3, and then we will again go towards west. Now you can see that this point, this quantity 2 here, and this is the quantity 3 here. So what we will put here is the minimum quantity of these 2 points, so that we will put the 2 here. And now again this column is also exhausted, and we have crossed this particular demand of D3, and now we'll have to go again towards the west of this particular cell, and here the column wise we have the amount 3, and row wise we have the amount 1. The minimum is 1, so we will put 1 here. This is 1, and again we have left 1 column, and the only 2 quantity remains in the particular row as well as in the particular column. So again we will put 2 here. So what happened in this particular case, by using that northwest corner method, so class, this is the northwest corner method, this is north and this is west, so that's why we particularly start from this particular column, that is north, and then we move towards west, then again we moved vertically, then again we move towards west, then again we fill this particular cell, again we moved that vertically. So that's why this process is known as a northwest corner method. And again in this particular case you can see that x11 is equal to 3 and x12 is equal to 2. These are actually the quantities or the amount of the products to be supplied from the particular supplier to the particular destination. Now class, let's repeat this particular example. Again there are 3 supply points, that is S1, S2, S3. There are 3 destination points, that is D1, D2, D3, D4. Now whenever we will use that northwest corner method, we will always start from this particular cell, and we will compare row wise value and column wise value, that is 3 and 5. The minimum value is 3, so we will put that value 3 here, So we will cross this 3 because that demand is being met. We cannot add any other value in this particular column because we will have to satisfy that total demand and total supply condition up to the end of this method. So we will again cross this 5, and because there are 2 points from this particular supply S1 available here. Now after writing that 3, we will move towards west, that is horizontally, and we will again compare the column total, that is 5, and the row total, that is 2. So minimum is 2, we will write 2 here, and again we will subtract 2 from here 3 because now there are 3 more units required at this particular destination, as we have already supplied 2 units. So we will cross this particular value here, and again we will move column wise. Column total is 3 available here, and row total is 6. So we will write the minimum value here, that is 3. So again this 3 is exhausted, and we will minus this particular 3 from this particular value. So we have 3 units available from this particular supply now, and again we will move towards west, and 2 out of 2 and 3, the minimum value is 2. So we will put 2 here, we will cross here, and we will less this quantity by 2, that 1 will remain here. Now again we will move towards west, and now there is only 1 point available here, row wise, and column wise 3 is available here. Minimum is 1, so we will put 1 here, and now we will subtract the 2, we will subtract 1 from this value, and it will become 2. And now we will write again, we will move vertically and write 2 here. So all the demand and the supply conditions are satisfied. And again class, when we will use this method, you will have to be very careful that your total should not be disturbed. Now you can see that the total here is 3, here is 5, here is the total is 2, and row wise the total is here 5, the total here is 6, and total here is 2. So we have not disturbed any of the total for our supply and destination. So this is the way to fulfill this particular table by using northwest corner method, and this table actually gives you some initial solution. We will discuss how we compute the initial solution in the next lecture. So this is the first method of filling this table, that is the northwest corner method. There is another method available, that is the least cost method. Now what we do in this particular method, we will not start from the first column as we did in northwest method. What we will do, we will start from that particular cell where the per unit cost is minimum, and again we will compare the column total, we will compare the row total, and we will write the minimum available value at that particular cell. And then again we will not move northwise or costwise, and again we will not follow that northwest rule, but we'll follow the lower cost rule, and we will move towards that cell where the cost is lower. So that is about the least cost method. Let's discuss this particular method. Now suppose class, this is the table, and again there are the different supply points here, which may be S1, S2, S3. There are some destination points here, that is D1, D2, D3, D4. Now what we will do, we will start from this particular cell. Now why we will start from this particular cell? As you can see that in the small squares the different costs are given, that is the per unit cost from a particular supply to the particular destination, and this is the least cost available, that is 1. So that's why we will start from this particular cell, and again for this particular cell we will compare the column total, we will compare the row total, that is 8 and 10. What is minimum? 8. So we will write 8 here at this particular cell. Now we will move to this particular cell. Now why we move to this particular cell? But again, before moving to this particular cell, we'll have to cross this particular value, because all the demand has been fulfilled. We cannot add any other value in whole of this column, and again we will subtract that particular value from the total value here, and it will now become 2. Now class, in this particular cell, again we will compare the column total, that is 12, and the row total, that is 2. What is minimum? 2. So we will write 2 here, that is 2, and again we will subtract that particular amount from the row as well as the column, as all the supply has been exhausted here. So we crossed here. It means that we cannot add any other value in any cell of this row, because that may disturb the total, and we cannot disturb the total of the demands and the supply. So class, now we will move to this particular cell, because it has the least cost among the other cells available, that is $2 or 2 rupees. So again, for this particular cell, we will compare column total, that is 10, row total, that is 5. So we will write the minimum value here at this particular point, that is 5, and accordingly we will subtract the relevant values from the row total as well as from the column total. Now in the column 5 is available here, and we have crossed this particular row. Now we cannot add any other value in this particular row. Now we will move to this particular cell. Now again compare column total 5, row total 15. So we can write 5 here, and again it will be crossed and it will be minused by that particular amount 5. And now we will move to this particular cell, that is 4, and again column total 4, row total 10, and we will write the minimum amount, that is 4 here, and the last cell available here is 6, and again we will write the 6 here. So in this particular fashion, by using the least cost method, we can always fill this table, and you will be able to find some initial solution by this particular method of least cost method. Now class, again this is the table, and try to fulfill this table, and we have just discussed and we have just solved this table. So if we use again that particular least cost method, what we will do, we will write 8 here, because we have started from this particular cell, because its cost is minimum among all the other costs. We will cross this 8, and the available supply at this particular point is now 2. Now we will move to the other cell, that is this one, and we will compare the row total and the column total, that is 12 and 2. So we will write the minimum amount here 2, and we will subtract from the particular relevant column and rows. Now it has been exhausted, so we cannot write any other value in this particular row. Now again we will move to this particular cell, because of the least cost, that is 2, available among all the other cells, and again we will compare the column total 10, row total 5. So we will write 5 here, it will remain 5 here, and it will again exhaust it, so we will cross this particular value. Now class, again we cannot move this particular cell, because it has been exhausted, and we cannot add any other value in this particular row. So we will move in this particular cell, where the cost again is minimum 3, and we will compare the row total and the column total, that is 5 and 15. Minimum is 5, so we will write 5 here, we will cross it. Now the supply here is 10. Again, now we will move to the next available column. We cannot write any in this row, we cannot write again in this particular row, and we can only write in this particular cell. Now we can again compare the column total and row total, that is 4, that is minimum out of these two values, and again this has been exhausted, and it will remain 6. And now as the last option we will write 6 here, so that this destination, demand, and this supply can also be exhausted. Now again supplies, when you will now again students, when you will fulfill this particular requirement. So again students, when you will fill this particular table, you should always be aware that your demand total and your supply total should not have been disturbed. If it is disturbed, it means you have do something wrong. For example, 5 plus 2, 5, that is the 12. 3 plus 8 plus, so that is 8 total row, column total is 8 here, column total 4 here, column total 6 here. Similarly, row wise total 5 here, row wise total is 10 here, and row wise total is again 5 plus 4 plus 6 is 15 here. So your total supply and total demand is not being disturbed here. So this is the way we can fill the initial transportation table by using either the northwest corner method or least cost method. And in the next coming class, we will try to solve the relevant problems, and again we will try to find out that how we can achieve the optimal cost in this